Given are the graphs of y1 equal to the square root of the quantity x plus 2 minus 4, and y2 equal to 1/3 x squared minus 10/3. In part A, what are the points of intersection? The points of intersection are the 2 points where these two graphs intersect. They happen here at -1, -3, and at 2, -2. In part B, use the graph to solve the equation the square root of x plus 2 minus 4 equals 1/3 x squared minus 10/3. To use the graph to solve this equation, we need to recognize that the left-hand side of the equation is exactly the same thing as the graph of y1. And separately, the right-hand side of the equation is exactly the graph of y2. So when we are asked to solve this equation using the graph, we need to recognize we're looking where these two values, in this case y1 equals y2. To put that another way, we're looking for the point of intersection of these two graphs. But in looking for that point of intersection, we need to recognize that the original equation did not have any y values in it. The original equation was the square root of x plus 2 minus 4 equals 1/3 x squared minus 10/3. Since the original equation only had x's in it, the solution for this equation must also only be x values, so it becomes the x values of these points of intersection. So the solution to this equation is the solution set -1, 2. That is the solution set because those are the x-coordinates of the 2 points of intersection, -1, -3, and 2, -2. In parts C and D, we're going to be looking at 2 separate inequalities. Please note that there is this URL down here with a link to a Desmos graph that is an interactive version of what we're already looking at in the video. So to answer the next 2 parts, we will make use of that Desmos graph. In part C, we want to highlight the portions of y1 equal to the square root of x plus 2 minus 4, where the square root of x plus 2 minus 4 is greater than 1/3 x squared minus 10/3. Before we do that, we want to remind ourselves that the left-hand side of this inequality, that square root of x plus 2 minus 4, is exactly the red y1 graph. And the right-hand side, the 1/3 x squared minus 10/3, is exactly the blue y2 graph. So another way to phrase what it is that we're trying to do is we're trying to figure out where is the y1 greater than the y2. We need to keep in mind, though, this is a reference to the y values being greater than, or the y values being equal, or the y values being less than, whatever the equation or inequality happens to state. So to begin answering this, we will shift over to the Desmos graph to begin using that interactive aspect of it. Now when we first load this interactive graph, it will be active. The slider in the 3rd row on the right will already be animated. What we're going to do is grab hold of it and start it back at the beginning where x1 equals -6. Now what we're trying to do is compare the y values on the blue graph to the y values on the red graph, or the y values on the parabola to the y values of the square root graph. As we begin sliding from the left to the right, starting at -6, you'll notice all the way up to, say, -2.1, there is no point on the red graph. That's because the red graph, the square root graph, does not exist at that point. But starting at -2, there are points on the red graph. That is the first x value that will give us a real solution or a real y value from that calculation. And at this point, you will notice that the red point is vertically below the blue point. This means that the y1 value is below the y2 value, or that the square root of x plus 2 minus 4 is less than the 1/3 x squared minus 10/3. But if we continue sliding further to the right and stop at x equal to -1, you'll notice we hit that point of intersection that we identified in part A and used for our answer in part B. At this point, the square root of x plus 2 minus 4 equals the 1/3 x squared minus 10/3, or y1 equals y2. But if you remember, what we're looking for in this particular inequality is where the square root of x plus 2 minus 4 is greater than the 1/3 x squared minus 10/3, meaning the y1 point will be above the y2 point, or in terms of colors, the red point would be above the blue point. If we continue moving further to the right, from x equal -1 to say 0, you'll notice at this point the red point is above the blue point vertically. This is telling us that x squared plus 2 minus 4 for this x value is greater than the 1/3 x squared minus 10/3 for this particular x value of 0. And it stays that way until we get to the next intersection point, at 2, -2, the other point of intersection we identified earlier in part A and B. And from that x value on to the right, from 2 to 3 to 4, forever on to the right all the way towards infinity, the red points will stay below the blue points, meaning that the y values from the square root will be less than the y values from the x squared. Now taking this back to the lecture packet, we need to remind ourselves what we're trying to do. We are trying to highlight the portions of y1 equal to the square root of x plus 2 minus 4, where that is greater than 1/3 x squared minus 10/3. Well, what we just discussed on the Desmos graph is that that was happening in this portion, between -1 and +2, because that's where the red graph is above the blue graph. But looking at the inequality that we are trying to solve, and recognizing there are no y's or y variables used in that inequality, they're only x's, we need to take this highlighted portion of this graph, between -1 and 2, and bring it up to the x-axis. If I were to highlight that on the x-axis, I would highlight everything from -1 up to 2. And that highlighted portion right there is the beginning of our interval notation answer. We would be including every x value from -1 up to 2. But what we also need to include in this interval notation is whether -1 or 2 themselves are solutions for the inequality. Given that our inequality is strictly greater than, we need the red graph to be strictly above the blue graph, and at x equal to -1 or x equal to 2, the two graphs are intersecting, we do not want to include -1 or 2 as solutions for this inequality. So for the interval notation, we would put parentheses at -1 and parentheses at 2. So to fully state that interval notation, the solution set for this inequality in interval notation would be the interval from -1 to 2, not including the -1 and not including the 2. To write this out in set builder notation, the set builder notation would begin, this is the set of all, in this case the variable is x, so it is the set of all x such that, or where, and now we need an inequality using x's and numbers and inequality symbols to capture what it is that we want. Well, one way to describe what we want is that we want x to be between -1 and 2. So I could begin by writing that down. I could write a -1, between that I could write the variable x, and to the right of that I could write the number 2. Because that's literally what I want. I want my x values to be between -1 and 2. But we also need to express this using inequalities. This ends up being that double inequality in one. We need -1 to be less than my x values, or another way to say that is we need the x values to be greater than -1, and at the same time we need those x values to be less than 2. So if we add in two less than inequalities, -1 is less than x, which is less than 2, we capture the relationship that we're trying to state. X must both be less than +2 and greater than -1. In part D, we want to highlight the portions of y1 again, where y1 is the square root of x plus 2 minus 4, but this time where the square root of x plus 2 minus 4 is less than or equal to 1/3 x squared minus 10/3. If you want, go back to the interactive Desmos graph to play around with a bit to try to identify where this is happening. But for now, I'll stick with the graph that we have in front of us. Recognizing that that less than inequality means vertically below, so I need the y1 graph to be vertically below the y2 graph, I recognize that's happening at two places. It's happening on the left end, and it's happening on the right end. And putting that in terms of x values, it's happening between -2 and -1, and from 2 on to the right. If I bring that highlighting that I have on the red graph to the x-axis, because I'm recognizing my answer is going to be exclusively x values, I would be highlighting everything from -2 to -1, and everything from 2 to infinity. And again, those highlights become the foundation for my interval notation. There are two separate intervals here. One interval is from -2 to -1. The other interval is from 2 forever on to the right, meaning from 2 to infinity. But again, interval notation includes not only the endpoints, but a notation recognizing whether that endpoint is included as part of the solution set. So starting with -2, the square root graph ended at -2, and if I were to throw -2 into this inequality, it would give me a true statement. it would tell me that -4 is less than -2. So I do want to include -2 as an x value in my solution set. So it will get the square bracket. Now over at x equal to -1. The x value of -1 is where we have that point of intersection that we've used several times now. In this situation though, the inequality we're working with says less than or equal to. Because it includes that or equal to, we do want to include the point of intersection. So -1 for an x value is also a solution for this inequality. And again, we'll get a square bracket. Over at x equal to +2, we have exactly the same thing happening. It is the point of intersection, but because the inequality we're solving is less than or equal to, we want to include the points of intersection as well. So x equal to +2 will also be included. Now when we return to the notation, we have from -2 to -1, both -2 and -1 get square brackets. +2 also gets a square bracket. And infinity being a concept here, and not a number I could use in this calculation, it will get a parenthesis. It's telling me I can go further and further to the right, but I'll never actually get there. Now we need one more symbol to glue these two intervals together to say, together they make the solution set. So the way to think about this is as follows. I can either pick my x values between -2 and -1, or, and that word or is critical here, or I can pick them from 2 on to infinity. The way we capture the word or in this interval notation is with the union symbol. So that union would say, I can pick from -2 to -1, including either -2 or -1, or I can pick from 2 to infinity, again also including the 2. That is the interval notation way to state the solution set. The set builder notation of the solution set would be as follows. It would be the set of all x's, and again we're using x because our inequality only has x's in it, where, and here we're going to need two separate inequalities just like we had two separate intervals. So to describe the left interval from -2 to -1 using inequalities, I would want my x values to be pinned between -2 and -1. So I'll start out writing -2, then x, then -1. And because I want -2 to be less than the x, and x to be less than the -1, I will throw in less than. But I do also need to keep in mind, the inequality I'm solving is not less than, but less than or equal to. So -2 could be less than, or it could be equal to the x. So I actually want -2 is less than or equal to x, which is less than or equal to -1. Now, here's where the word or comes important again. We can either pick our x values between that, -2 is less than or equal to x is less than or equal to -1, or, and I need to write out the word or, the other option is that x is greater than or equal to +2. Again, the word or is critical. We need to represent that either we can pick our x values from here, or we can pick them from over there. Those are the two places where we can do this. Anytime we're going to have these split solution sets, split out into separate intervals, we will be using union in the interval notation, and we will be using the word or in the set builder notation.